Right, hello everybody. So today we're going to talk about kind of a generalization of all the quantum algorithms that we've seen so far. More generally, actually, more precisely, we're going to generalize the problems that we've seen so far. They all fit under this framework called the hidden subgroup problem. Okay, so let me remind you of some tasks that we've solved efficiently with a quantum algorithm so far. So this was maybe the first one. If you recall that far back, it was learning or discovering a secret XOR function. So this was due to Bernstein and Vazirani. And the story there was you're given, quote unquote, given a function capital F mapping little n-bit strings into single bits. And the way you're given it is like a quantum circuit that implements it. And you're promised that it's of a special form. It's basically an XOR function. Or in other words, it's of the form S dot product X for some mystery S. This is the mod 2 dot product. And your task was to find S. And we saw that you could do that efficiently with the quantum computer, something like little n gates. Okay, and then we saw a more sophisticated example. This was Simon's problem. And here you're again given a function mapping n-bit strings into some set that we just called colors. That set wasn't too important. Again, with the special property that it was L periodic. And this just meant that like all the domain elements were paired up as X and X XORed with L, or plus L in a mod 2 component-wise fashion. And you were promised that F had the same color value on these two pairs, and otherwise the color pairs were all distinct. And the task was to find capital L again. And we saw an efficient quantum algorithm for doing that. And then we subsequently studied a similar looking problem, but in a different domain. This is the period finding problem. So again, now you're given a function F mapping the integers mod some capital N into colors, some set. And it was promised to be L periodic. And in the cleanest version of the problem, L was like a number that divided capital N. And you were promised that it was L periodic, meaning that f of x equals f of x plus L mod n, f of x plus 2L mod n, etc. In order for this to make sense, L has to divide n. And then your task again was to find capital L. And actually, you can do this for any capital N. We saw it in the case when capital N is a power of 2, which in some sense makes the problem a little trivial, because there's not that many divisors of capital N in that case. You can actually do it for any capital N about equally efficiently. It's annoying because you have to do a quantum Fourier transform circuit that is not over a power of 2. You can do it, though. OK, and there again, you can find a quantum algorithm that was efficient in the sense that it used polynomially many gates in polynomial in little n, the log of capital N, the number of bits it takes to represent these numbers. And then finally, Shor's algorithm, you can think of it as kind of a little bit of a twist on this. The way I want you to think about it for this lecture, or you can think about it, is that the same story, you had a periodic function, but in some sense its domain was the integers. Remember, this was the function like a to the power of x mod b, where b was the number you were trying to factor. And this is a periodic function over the entire integers. And again, you were trying to find that period L. OK, it's an infinite domain, so we cannot represent infinite objects. But we kind of had this idea of taking like a really big slice of the integers from 0 to capital N minus 1, much bigger than the period, and just treating that as our domain. So in some sense, Shor was like similar to this, but with the domain being the integers. OK, so we saw quantum algorithms that could solve all these problems efficiently. And like very briefly, how did they work? Work by this paradigm we've seen many times. So the first step kind of loaded this like exponential amount of data into a quantum state with little n qubits, sort of the truth table of the function. And then it did a quantum Fourier transform, which was different in this case when the domain was, this is also a domain is sometimes referred to as the f2 to the n, the vector space of dimension n over 0 and 1. It was a different Fourier transform in this case than in this case, but it was some Fourier transform that you could compute efficiently with a number of gates that was growing reasonably with respect to little n. And then you used this quantum Fourier sampling paradigm. So you took the Fourier transform in some sense and then measured, which gave you a sample from the objects that index the Fourier coefficients. And we thought of these as kind of clues as to what the mystery L was or what the mystery S was. And in each case, and this was a little bit different in each case, we saw how to like take these clues, or our ability to generate these clues, and figure out the secret L or S. Okay, so that was the paradigm we saw 2 or 3 times already now. And so since we're now experts on this paradigm, it's like time to set it up in a general context so that we don't forget it and think about what else it could potentially do for us. So we're going to talk today about the common generalization of all these tasks, and that's this. It's called the hidden subgroup problem, or HSP. And we're going to ask 3 questions, or we're going to do 3 things. First thing is just define the problem and find this common generalization of the tasks that we've solved successfully so far. Okay, so that's defining what is this hidden subgroup problem. And then 2, we're going to ask for the more general version of all these problems, can we still do it efficiently with a quantum computer? So far we've had good success on that. Okay, and the last question is, we don't just want to generalize for the sake of generalization. We want to know, is this good for anything? So does solving, these HSP variants, help us for anything? And what we've seen so far, the answer is sometimes yes. So this Simon's problem didn't seem to really be good for anything, but it was pedagogically valuable. But then, this period finding or this variant due to Shor was great. It helped us solve the factoring problem efficiently. So, maybe we can find some other problems that can be exponentially sped up with a quantum computer via this framework. OK, so these are the topics we're going to get at today. So let me go over them. So I'll give you a quick preview of each of them, and then we'll dive into it. So first, what is this common generalization of all the problems? Well, in these cases, 1, 2, kind of 3, we have the same mathematical thing going on all the time. Like in the Simons, we have this set, which is 0, 1 to the n, and an operation, which is XOR. Or if you want to think about it mathematically, more, a different way mathematically, this is the vector space of dimension n over 2 elements, and this is the sort of component-wise plus operation, mod 2. In the period finding case, we had a different set as our domain. It was the integers mod n, and we had an operation which was plus mod n. This operation is the one that's always sort of going into the periodicity definition. And if you want to accept my alternative interpretation of Shor, here the set was like all the integers. And again, the operation was just, good old-fashioned plus. And what is a common feature here? Each of these pairs, namely the set and the operation, is what's called a group. Okay, that's an algebra term with which you may or may not be familiar. I'll tell you a little bit about them if you don't know that much about them. And actually, more than that, each of these guys is a commutative group. That just means that x plus y is the same as y plus x. But we're going to consider the possibility of groups where the operation doesn't commute. And actually, for each group, we're going to define the hidden subgroup problem. And so we kind of get a different problem for each group. And we've seen how to solve it in a few cases. So just as a quick warm-up here. So the hidden subgroup problem for a group, integers mod 24, which is basically an example of this when capital N is 24. So this is the integer 0 through 23. The operation is plus mod 24. So just to rephrase the problem, which we know about, it's right there in bullet point 3, but in this subgroup language. I'll explain this in a second, well, over the course of the lecture. The story here is that there's a subgroup. There's an object like the subgroup generated by the element 4. Okay, that's just refers to this, all the multiples of 4. And sometimes called H. And this is the case. This is what you should imagine if capital L happened to be 4. So this is kind of like a secret. Okay, here we said capital L, the period, was a secret, and now we're just sort of rephrasing things and saying this subset, which is going to be called the subgroup, the multiples of 4, is the secret. And once you define this, there's going to be something called the cosets of H, which are kind of like the translates of H. I'll explain this properly shortly, but these are all the sets that look like 1 plus H, which is 1, 5, 9, 13, 17, and 21. And there's 2 plus H. And there's also 3 plus H. Okay, and these are the sort of subsets on which, in this story, like f would have the same color value. Okay, so the setup here is that f has some color value on this set capital H, if L is 4, and a different color value on this one, and a different color value on this one, and a different color value on this one. And the problem you're facing here, just to restate it, again, in the case where capital N is 24, f is constant on these things called cosets. Okay, or you might call it now H periodic. This is what you're promised. This unknown function capital F takes one color on here, one color in here, one color in here, one color in here. And you have to identify 4, or you have to identify that the secret multiple is the one corresponding to 4. Okay, but this will be the hidden subgroup problem if you already know what these words mean, like subgroup and cosets, in like a more general setup. Okay, so that's a little story about what is the common generalization. Now let's talk about a little preview of whether or not this common generalization is efficiently solvable with quantum computers. Well, I'll give you the spoiler for what is now known about this story. Case 1, if the group is commutative, then the answer is yes. Okay, and we already saw that these were the 3 cases that we've solved before. They were efficiently solvable by a quantum computer in each case. And basically, actually putting together all the ingredients you already know is how one can solve this hidden subgroup problem in the case of any group that's commutative. So that's nice. Case 2, people were like, OK, let's get greedy and go to non-commutative groups. And I will, indeed, in just a second, tell you a little bit about bullet point 3, like why would we want to do this? But here's the basic story. I mean, the sad thing is basically the answer is going to be no. Or at least not no, but we don't know how. And I'll just tell you the story in words, and we'll get to it properly at the end of the lecture. You can try to repeat the algorithm that we've tried in this case of the hidden subgroup problem over non-commutative groups. And it starts out, you can start it out similarly. You have a function that maps a group to a set of colors, and you can think of it as a long set of data that you're trying to find some secret pattern in to do with subgroups. You can, again, load it into a quantum state with some little n qubits. And then the next step would be doing a Fourier transform. And we saw already that in these two different cases, we needed a different Fourier transform. This was the Hadamard transform. This was the classic discrete Fourier transform. And the Fourier transforms kind of go together with the group. It turns out that for any group, not just a commutative group, but any group, there is an appropriate Fourier transform. But it's mathematically a lot more sophisticated. It uses this stuff called group representation theory, which is, let's say, complicated. But there's some champs out there that have figured it out. And indeed, they didn't prove a general theorem yet. But for every, essentially every interesting non-commutative group that people have cared about, due to 3, they figured out how to build an efficient quantum circuit to carry out this Fourier transform. So that's great. So that step was done. OK, sounds good. And then what you're left with is this situation where, OK, you do now the appropriate quantum Fourier sampling. And you again kind of get clues as to what this hidden subgroup H is, this hidden periodicity in your data is. And that's the part where things have gone wrong, in the sense that basically in no cases, or let's say very few cases, OK, I should be fair, very few cases, but in no cases where it'd be really awesome, have people been able to figure out an efficient algorithm for turning these clues about the hidden periodicity structure into figuring out indeed what that periodicity is. So they haven't been able to do the analog of this last step, which was solving equations in this f2 to the n, or this approximate GCD thing that we saw in Shor. That last step of getting the answer from the clues, we don't know how to do that efficiently in any interesting case. Yep?
Does it make a difference for non-commutative if you have a normal subgroup?
Yes, it's actually known how to do it if you have a normal subgroup. If you know what normal subgroup means. However, there's one intriguing twist, which I'll get to at the end, which I'll explain more carefully, but to briefly say it. For this last piece of getting it loaded up into a quantum state and then getting clues and trying to figure out what the hidden periodicity structure is, we know there's a quantum algorithm that is efficient, that gives you enough clues that you can information theoretically figure out the answer H. We just don't know how to do it algorithmically efficiently. So this is a result due to Enger, Hoyer, and Knill. That sort of says, we know an efficient quantum circuit that gives you enough clues that in principle you could figure out the set capital H. But we just kind of don't know how to do that last classical clue solving part. So I'll explain what I mean more by that when we get to the end of the lecture. OK, so I told you a little bit about 1 and a little bit about 2. Let me tell you a little bit about 3 and whether, is there any point to this generalization, to this mathematical group business? And the answer is yeah, it's really useful in many cases if you can solve the hidden subgroup problem over different groups. So let me give you some examples. Brief summary is yes. So let's consider the hidden subgroup problem for different groups. And in each case, try to think of some applications. Okay, we don't really care about the HSP per se, but we do if we can do something with it. All right, so let's review the cases that we sort of saw. One is, 0, 1 to the n is the group, and the operation is XOR. Or you can think of this as f2 to the n, and the operation is component-wise addition, mod 2. And what do we get out of this? Well, we got Simon's algorithm. Well, that didn't really have any applications. It had an application of pedagogy, so that's good. But all right, this one was not so amazing as far as we know. OK, and then we studied this group, the integers mod n with the operation plus mod n. And here we got period finding. Well, this was actually also not really that interesting. But it was closely related to what you might call the grouping all the integers with the operation plus. And this gave us Shor's factoring algorithm. So that was awesome. Actually, Shor in his paper had another equally awesome application that we didn't talk about, but I'll say it. You can look at the group that's like Zn cross Zn. Briefly, this is all your elements, your domains are just pairs of integers, mod n. And it's kind of like this. The operation is adding them component-wise, mod n. OK, that's another commutative group. And Shor showed how to solve the hidden subgroup problem for this group, for a particular kind of subgroup. And this led him in the same paper to get an efficient quantum algorithm for this problem called the discrete log problem. Discrete log problem is you're given the multiplicative group of integers mod a prime and a generator of the group, and then you're given an element of the group which is known to be some power of the generator, and you have to figure out what is that power. OK, if you didn't catch all that, it's OK. But it's some problem that's used a lot in cryptography because it's assumed to be hard for classical computers to solve. So it's very much like factoring. It's a number theory problem. It seems really hard to solve with a classical computer. Our best algorithms are exponential time. And it's the basis for crypto systems like Diffie-Hellman and El-Gamal and stuff. And so Shor, kind of like these are riffs on each other, also shows how a quantum computer can solve that efficiently. OK, so it kind of ruined both these cryptographic applications if you have a quantum computer. And there's one more example of a similar flavor. And I put this one also in quotes. You can consider the group of real numbers with the operation addition. And you can ask the hidden subgroup problem for this setup too. Now, again, it's a little bit fishy like this one because we can actually not store an arbitrary real number in bits. So like with Shor, ultimately when you get down to the hardware, you have to discretize the reals. And so it becomes sort of like Zn again with a very large value of capital N. But your periodicity here is maybe not even with respect to an integer. It's with respect to some arbitrary real number. I won't say too much more about that. But as an application, you can get an efficient quantum algorithm for implicitly solving Pell's equation. And I won't really say what that is, but it's some kind of problem in number theory, which was not super famous, but it was known and related to cryptography before quantum came on the scene. And in fact, it was known that it was stronger than the task of, harder than the task of factoring. And Hallgren in 2002, by analyzing HSP and solving it on this group, the reals with operation addition, showed how quantum computers can efficiently solve this problem.
What does it mean implicitly?
If you know Pell's equation, it's x squared minus d times y squared. You want to solve this for positive integers x and y, where d is the input. And you even want to just find the smallest solution, because there's infinitely many. Trouble is the smallest solution may actually have exponentially more bits than d. So you can't even make sense of the question of just solving it, because the answer might take you exponential time to write down. But there's a sensible version of the task where you compute the nearest integer to the natural logarithm of the smallest solution. Which sounds funny, but there's a sensible reason for doing that. And then you can potentially do it because that only requires polynomially many bits to output. OK, so yeah, here's another problem that we know how to solve exponentially faster with a quantum computer than with a classical computer. Now, coming back to what I said on this board, if you know a little bit, you may notice that these are all commutative groups. And we have all smiles because we know how to solve this problem efficiently on a quantum computer and therefore get all these applications. Now, what about these non-commutative groups? So I'll continue the table here. And I'll only give 2 entries in this table. But they're both spectacular applications of the hidden subgroup problem. Downside is, as I said, we don't actually know how to solve it. But it's motivation for wanting to solve it. And since we had so much success solving the hidden subgroup problem for commutative groups, and in some other cases, like when the subgroup is like a normal subgroup, whatever that is, this is like a good angle for hope, maybe, for something like awesome that a quantum computer could do. So one group of interest is called the dihedral group. I'll say what that is later. It's like a group of symmetries of the cycle graph. And if you could solve the hidden subgroup problem efficiently for this dihedral group, then as an application, you would get an efficient quantum algorithm for the approximate shortest vector problem in a lattice. This is due to Regev. And if you don't know exactly what this is, you might be like, well, I don't know what that is, and like, is it better than this? It's much better, and I'll tell you why. So, as you may know, quantum computers can solve factoring, and therefore it made people really nervous for cryptography because most of the cryptographic protocols are based on the presumed hardness of factoring and discrete logit stuff. So people are like, boy, we should try to come up with some post-quantum cryptography, some cryptography that could be secure even if quantum computers really get built. And there's an extremely, extremely successful theory of cryptography based on lattices, lattice problems. Okay, lattices are grids in space that have a regularity pattern. And in particular based on the hardness of problems that look like this. You're given the basis of a lattice, and you have to find the shortest vector in the basis. And it's also intimately connected to this learning with errors problem that maybe you heard about due to this Mahadev paper that came out recently about certifying quantum computations. So it's an extremely successful theory for post-quantum or cryptography. And it's actually even good regardless of quantum computers. There are cryptographic things you could do with hardness based on lattices, like fully homomorphic encryption that we don't even know how to do, assuming hardness of factoring and stuff. So some kind of even better version of cryptography than the kind you might know about. And Regev showed that if you could solve the hidden subgroup problem on this dihedral group, it would crack this problem and probably ruin all that cryptography. But luckily, we don't know how to solve the hidden subgroup problem efficiently with a quantum computer. But there is some progress, well, a mild amount of progress, but it kind of shows that something non-trivial is going on. Kuperberg showed that you can solve this problem in 2 to the square root of little n time, which is still exponential, but the fastest classical algorithm is more square root of 2 to the n, 1.4 to the n. So perhaps something could be done. OK, I'll mention one more well-known non-commutative group. It's the symmetric group. This is the group of all permutations of n objects or letters. And if you could solve the hidden subgroup problem efficiently for this group, which we don't know how to do on a quantum computer, you would get an efficient algorithm for the graph isomorphism problem. This is a very famous problem in theoretical computer science. Given 2 graphs and vertex graphs, are they isomorphic? Are they the same graph up to permuting the variable names? And we don't know how to solve this problem in polynomial time, classically. And for a long time, the most efficient algorithm we knew was something like 2 to the square root n time. And then a few years ago, there was a very, very famous result where Babai showed that you could solve this problem almost in polynomial time in something like n to the log n to a constant time. So on one hand, maybe that makes the motivation here a little bit less. The motivation being that if you could solve this hidden subgroup problem efficiently in polynomial number of steps on a quantum computer, you get a polynomial time algorithm for graph isomorphism. You might say, well, we almost have one. This is kind of good. But I think it's still reasonable because, first of all, Babai himself believes that you cannot do it faster than n to the log n. So I think he doesn't think you can solve it in polynomial time. But maybe you could do it with a quantum computer, which would be interesting. In fact, this reduction from graph isomorphism to the hidden subgroup problem in the symmetric group is quite easy. I don't have time to explain it today, but as with many things, it will be on the homework. So you'll really see, I think, the connection there. There's also something I think is really highly intriguing about all of this and about quantum computing in general, which is that there are very, very few problems in theoretical computer science, in algorithms, which have this status where we don't know how to solve them in polynomial time, but we also don't know or don't think that they're NP complete. I mean, almost all problems seem to either be solvable efficiently, or they're NP complete, which means probably not solvable efficiently. There's very few problems that are in this gray zone. And it's pretty much exactly like factoring, discrete log, lattice problems, graph isomorphisms. So it's kind of amazing to me, miracle, that these are the exact problems which quantum computing either can solve or maybe there's an angle for solving. How is it that so amazing that this new quantum computing came on the scene and it didn't solve the NP complete problems and it didn't just solve the polynomial problems, it went right for this crazy gray zone we had previously developed. That's amazing. OK, so that's the story. And now I'll get into some details, like what's a group and stuff like that. Any questions? OK, so right, what's a group? So on one hand, maybe you know. On the other hand, you don't know. I'll give this very fast, incomplete overview. We'll see what we can do. Hopefully this is enough motivation for studying this problem at this level of generality. All right, so groups, briefly. Okay, so groups are an algebraic structure they have in math, rings and fields, and then there's one called groups. So a group, as we've kind of alluded so far, consists of two things: a set, or a domain, usually called G, which is the integers mod n, the integers, the reals, whatever. And an operation, a binary operation, which I'll call circle. And what is that? It takes two inputs and spits out one output. And these inputs and outputs are elements from your set. So it takes two group elements and outputs a group element. And just like with these algebraic things like fields and vector spaces and so forth, there's a bunch of rules. So there's 3 rules for a group about what this operation has to satisfy. So rule number 1 is that if you write this with it looks like the operation applied to 3 things, that should make sense. And formally, what that means is that it doesn't matter where you put the parentheses. If you do y and z and then operate x, it should be the same as doing x and y and then doing the operation z. OK, this is associativity. It's a basic property of, the plus operator in many circumstances. 2, there should be a neutral element or an identity element, which is the element which, if you do the operation with it, does nothing. So there's a neutral element we'll call E, such that E applied to x equals x, and also x operating with E equals x, and this is for all x. OK, so that's going to be the number 0 in this case, the integers mod n. And 3, every element should have an inverse element. So for all elements, x in G, and you should think of this as the negative of a number. there exists some inverse element, which I'll call x prime. Usually people call x to the -1, but I'll call it x prime in G, such that it kind of cancels with x in the sense that x operation x prime is the neutral element, the identity element, and also the other way around. Okay? So anytime you have a set of objects in a binary operation that satisfies these three rules, it's called a group. And I mentioned this in words. One property that you might have thought of including is commutativity. But we don't include that necessarily. So we don't necessarily insist that x operation y equals y operation x. Okay, it may or may not, your operation may or may not have that property. If it has this extra property, commutativity, it's quite nice and it makes your group more simple, but we don't insist on it. Okay, well, we have some examples up here, so let's just talk through them. So all of these, pairs are groups. So let's see. So the binary strings with the XOR operation, the component-wise XOR operation. Maybe it's easier to think about it like this, because then it's clear that addition is associative. Everybody knows that fact. So the neutral element here is the all zero string. If you add in the all zero string or XOR in the all zero string, nothing happens. And what is the inverse of a string here? It's just the string itself. Because if you add a string to itself, mod 2, you get the all zero string, which is the neutral or identity element. Okay, this is maybe the easiest case. This is the integers mod n is the G, and the operation is plus mod n. The neutral element is 0, and the inverse of x is negative x, mod n, because x plus negative x is 0. Okay, integers, same story. The neutral element is 0. The inverse is negation. Let me just look at this case, actually. Here the domain, or the set G, is all pairs of numbers, where you regard the numbers as mod n integers. And the operation is like component-wise addition. So you add mod n in both sort of coordinates. Okay, and in this case, the neutral element E is the pair 0, 0. If you add 0, 0 to any pair AB, you get back AB. And the inverse of x, y is minus x minus y. Okay. Actually, it's a fact. Let me just erase some stuff here. Actually, let me give you one more example of a commutative group. It's one that we thought about yesterday, or not yesterday, last time in the Shor's algorithm, the reduction between factoring and order finding. One more example is G is the set of integers mod B, that have an inverse, a multiplicative inverse. This is all the integers mod B that are co-prime to B. And now the operation here is times mod B. And now the neutral element is 1. And the inverse of an element is, like its reciprocal, mod B. Okay, so I think even on the homework that you check that sort of all this makes sense. And this is another example of a group, and it's actually a commutative group too, because x times y equals y times x, mod B. So let me tell you, it's a fact. It's not extremely hard to prove, but not extremely easy either, that all finite, and here I mean, the set G is finite, commutative groups are basically the same as, up to just renaming the elements, things that look kind of like this one. Look like integers mod n1 cross integers mod n2 cross integers mod n k. Okay? So basically, every finite commutative group looks like, you have like a tuple of integers, and for each coordinate, there's like a modulus, which can be different for them. And the operation is addition, component-wise addition, where you do it, mod n1 in the first coordinate, mod n2 in the second coordinate, and so forth. Okay, so in some sense, the finite commutative groups are not an extremely rich set of objects. I mean, they're basically, riffs on these three things. Any questions so far? OK, so let me just tell you what are these two non-commutative groups. All right, I'll erase this even though I just wrote it. OK, so I'll start with a symmetric group. It's a little bit easier to explain. Well, they're both pretty easy. But it looks different in the sense that, like, in all these groups, like, the objects are somehow basically like numbers. But like in these two groups, like, the objects, the set G is like not a set of numbers at all. It's more like a set of operations, which is a little bit confusing. So the symmetric group, which is sometimes notated S sub n, is this. G is the set of all permutations of the numbers 1 through n. So pi, mapping the numbers 1 through n into the numbers 1 through n. OK, that's the set G, all the pi's. So it has n factorial different elements. And the operation circle is, well, like composition. What do I mean by that? It means that like pi, circle, sigma, if these are both permutations, this means the permutation, the new permutation, which is like first do sigma, it's out of order, and then do pi. Okay, so if you like, sigma is some permutation, pi is some other permutation, you'll get a third permutation if you like first do sigma and then compose it with pi. Okay, and that's the operation in G. And it's function composition, which is why it's associative. And the neutral element is just a permutation that does nothing, basically. It's the one that maps, 1 goes to 1, 2 goes to 2, n goes to n. Obviously, it does nothing. And then like every permutation has an inverse permutation. OK, so it satisfies all the rules. It's not commutative, though. As you can check with this little example I leave to you to play around with. If we do like 1 goes to 2, 2 goes to 1. Here, let's let n be 3. And 3 goes to 3. Let's call that pi. Versus, how about 1 goes to 2, 2 goes to 3, 3 goes to 1. We call that sigma. Then you'll check that you get like different permutations if you do it in different orders. Like if you do it like you're supposed to, and 1 goes to 2 and then goes to 1. So 1 goes to 1. 2 goes to 3 and then to 3. So like this thing is 1 goes to 1, 2 goes to 3, and then 3 goes to 2. But if you do it in the other order, well, you'll get a different result. I'll let you think about that while I write. OK, last one I want to tell you about is this dihedral group. So I'll also define that briefly. It's another non-commutative group. It's usually notated d sub capital N or d sub 2 capital N. So this is the group where G is it's kind of, well, to use terminology I'll explain in a second, it's a certain subgroup of this. It's just some of the permutations. All the permutations that are automorphisms, to use a fancy word. So you can think of it as self-isomorphisms. of the cycle graph. So this is one of the simplest of all possible graphs, the cycle with n vertices. And think about this in the context of that graph isomorphism problem. There's some ways you can rename the vertices here such that you'll get back the same graph. Like if you just do 1 goes to 2, 2 goes to 3, 3 goes to 4, and so forth, then you'll get the graph that's like 2, 3, 4, 5, dot, 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 n minus 1, 1. And that's the same graph. So that permutation, which is called a rotation, goes into the dihedral group. And also if you sort of draw this picture and like do the reflection through this line, like 2 switches with 1 and 3 switches with n and so forth, that's another permutation of the vertices that preserves the structure. But there are other permutations that don't. Like if you just switch 1 and 2 and leave everything else the same, you get like a fundamentally different graph, because in the new graph, 1 is connected to 3, but it wasn't connected to 3 in the old graph. OK, so the operation is the same, by the way. It's like composition of these things. OK, and really, this is actually a rather small group. I mean, all the permutations is, this should be capital N, would be capital N factorial permutations, but most of them don't actually leave this graph unchanged. In fact, the size of it is only 2 times n. Because to be precise, what are the permutations that leave the cycle graph unchanged? There's kind of like n minus 1 different rotations. And there's the neutral permutation that just leaves everything the same, or you can think of that as like rotating 0 times. So that's n operations. And then there's also n reflections. So there's 2 times n operations. OK, so that's like an example of a group. OK, so now I have to tell you what are subgroups. Well, the simplest way to describe it is if you have a group, G, with a binary operation circle, a subgroup is like a subset of G, which is still a group in the sense that it still satisfies all these properties when you like go over just elements of the subset H. But let me describe it in a little bit of a different way, which will, I think, help for the explanation of this hidden subgroup problem. And again, it's good to keep in mind here an example, a running example, which will be G is the integer is mod 24, and the operation is plus mod 24. So here's one way to think about subgroups, especially in finite groups. So let's say you have this group, and you like take any old element in it, which I'll call little h. OK, so if you want to follow this running example, think of little h as being 4. Then I can define a thing called the subgroup generated by little h. That's the whole name. Generated by little h. And what does it mean? I'll just say it in words. You basically start with the neutral element, which is 0 in this case. And then you just like start adding in, or like operating in, like h and h inverse as much as you can. And just keep doing h as much as you can, and just find all the elements that you get in that way. OK, so it's basically, you start from the neutral element, which is 0 here. OK, and you'd like take h, and like h operation h, and h plus h plus h, et cetera. And you also use the inverse. And you just like keep doing that as much as possible. And that's your set, capital H, the subgroup generated by little h. OK, so in the example, you start with 0, the neutral element, and then you do plus 4, and then plus 4 again, and plus 4 again. And you can also do minus 4, but it's going to be the same, as you'll see. 16 and 20, and then you keep doing it, and you get back to 0. So that's it. That's the subgroup generated by 4. And you can also have subgroups generated by like 2 elements, or any number of elements. Let me just do the example of two elements, h1 and h2. You can have any number of elements. But what does this mean? You take any old h1 and h2 in your group, and the subgroup generated by them is you again start with the neutral element, E, and you just go crazy like applying or like operating in h1 and h2 in any order and also with inverses. Okay, so you just get like h1 and h2 and h1 circle h1 and h1 circle h2 and like so forth and so on, and h1 prime and h1 prime circle h2, and okay, just like put them all together as much as you can. And that's it. So I gave you one kind of explicit example here of a subgroup generated by one element inside this group. There's actually an example of a subgroup generated by two elements already on the board. So if G is the set of all permutations, we can actually just let little h be the permutation that does, let's consider little h to be the permutation that does 1 goes to 2, 2 goes to 3, 3 goes to 4, etc., and n goes to 1. And that's kind of like the rotation operation here. Okay, so if you just keep adding that to yourself, you'll get like n different elements. And then if you take that as your h1, and as your little h2, the single permutation that swaps 1 and 2, and swaps 3 and n, and swaps 4 and n minus 1, this kind of reflection permutation. And you start applying those two things in like all possible ways, the rotation, the single rotation and the single reflection. It's not hard to show that you'll exactly get this collection of elements, all the 2n elements that preserve this cycle. Okay, so that's a handy example on the board where you have a subgroup. This is a subgroup of this one generated by two elements, a rotation and a reflection. Okay, so that's subgroups. There's one more terminology we have to define in order to define the hidden subgroup problem, and that's cosets. And cosets are extremely similar to subgroups. So cosets are basically like translated subgroups. Okay, so what do I mean by that? So let's say you have G. And I've drawn G as a square. I mean, think of a square full of dots that are like all the elements of G. Okay, whatever. And say H is the subgroup generated by, I don't know, I'll take two elements, H1 and H2. Okay, it can be generated by any number. Let me just take 2 as an example. So we know what is H. It's like you start at the identity or the neutral element E, and like you operate in, add in H1, and that takes you to some new element, and you add in H2, that takes you to some new element. And you also start adding in H1 and H2 and also H1 inverse. Okay, so you kind of walk around on all the elements by this operation of circling in H1 and H2 and their inverses, and you collect up some set of the elements. Okay, and that's called H. Okay, that's just what I told you over there. And it's some subset of the elements. And the coset of H with translate X, where X is any element of the group. This is not the real term. Usually they call it representative, but I'll call it translate. Is the same thing, but you just start at X rather than the neutral element. Okay, so you just play the same game. Let's say X is this element right here. You just start doing X circle H1 and X circle H2, and start adding all H1 and H2 to these guys. Okay, and you collect up another set of elements. And perhaps this is like some funny picture, but perhaps you collect up all these elements. And that's called the coset of H with translate X. And the notation is, suppose I should have did it on the left-hand side. It actually makes a difference, believe it or not. The notation is XH. Okay, so this is like a subset of the elements called this coset. So maybe this box is all of XH. So let me do an example, one of the simplest examples. In fact, let me do an example where it's a subgroup only generated by one element, namely this example. OK, so for EG, when G is Z mod 24, the operation plus, H is, I'll use this notation, the subgroup generated by 4. So this one right here. The coset of this H, I know it's a little bit mathy, but translate 1 is, you just start from 1 and like add in 4 in all possible ways. So it's like 1, 5, 9, 13, 17, 21, and then you're done, because if you add 4 again, you get back to 1. OK, and with translate 2, you get 2, 6, etc., up to 22. With translate 3, you get 3, 7, up to 23. And with translate 4, you get, like, well, you start at 4, 8, 20, and 0 again. Hey, that equals H. So that can happen. And you can keep going, right? You actually have one for every group element. So with translate 5, well, you get this one again, right? It's the same as this one, 1, 5, 9, etc. So actually, you see that, like, as you consider all the possible translates, often you get the same set. And by the way, just to connect this back to, like, period finding, right? In period finding, you had this like function capital F that mapped, in this case, the numbers mod 24 into colors. In the periodicity condition, if the secret period was 4, was precisely that like F took one color value on this set, one color value on this set, one color value on this set, one color value on this set. Okay, so that's like what's going on here and why we're introducing these definitions. OK, so we're almost done with definitions. So here are some facts which are very easy to prove, but I won't spend the 2 minutes to prove them. Like genuinely, they're like exercises that you could do in a couple of minutes. So one is all these cosets, like XH, have the same size as H. OK, we saw that here. The coset really just looks like H itself, but translated. Okay, another fact that we saw here is that any two cosets are either identical or disjoint. So if you look at x1h and x2h, they're either the same or disjoint. OK, and we saw that here too. All these cosets are the same or different. And in fact, every element is in some coset. So the cosets partition G. OK, so pictorially, I mean, I didn't do this by accident. All the elements of G get split up. Once you fix H, like this box that contains the neutral element, all the elements of G get broken up into, like, maybe this is y times H, and this is z times H for different translates x, y, and z. OK, and as you go over all group elements, I mean, if you start with any element in this box and translate H by it, you get this self-same coset, and so forth. Okay, so the cosets break up G into like equal-sized sets of elements, but in some structured way, not just any random way. Okay, and now finally, we can say that if you have some function f that maps a group to any old set called colors, we say it's H periodic for H a subgroup. You know, if f has the same color value on if for all cosets x, h, f has the same value on all elements in x, h, and f gives different colors to different cosets. Okay, so a priori, capital F, if you have this set group G represented by these dots, you could have any function that puts a color on each dot, but it's H periodic if it gives all these red, all these green, all these blue, all these yellow, or something like that. Okay, and that's exactly like the scenario that we saw in, let's say, period finding problem, right? You're given like a function f that gives a different color to each one of these translates, and you have to figure out in that case what is the common value here. What is the subgroup H defined by 4? Okay. All right, so now we can finally kind of get back to quantum. So the hidden subgroup problem for G, a group, so it's actually a family of problems, one for every possible group, is, well, you're given QF implementing an H periodic function. But H is like a secret to you. Find H. Just a small word here about like actually representing objects on computers. G can be any old group. Like if it's a symmetric group, it has like n factorial elements. You have to like name them using bits somehow. So when I say given, right, I'm assuming that like you have some scheme for like naming the elements of G, and it's like a reasonable scheme, by something like log cardinality of G many bits. Okay, so we assume you have some scheme for like naming the group elements, and that's what QF takes in as input. And then finding H also means like find generators for H. Okay?
Well, that could happen that like H has exponential generators.
No. So it turns out that every group of size m has a generating set with at most log m elements in it.
Right. Okay.
So then it's a plausible. There will always be like a efficient to write down generating set. Okay, so let me just say in words, hopefully it's clear by now, how this generalizes the previous problems. For example, like in Simon's problem, your group was 0, 1 to the n with XOR. And actually, you were sort of promised that it wasn't any old H actually in Simon's algorithm. It was actually always generated by a single element. Some secret L. And actually then in particular that means that H is super simple. It's just 0, the identity, a neutral element, and L. And so the cosets are like the quote-unquote translates of this. They're all things that look like x, comma, x plus L. Okay, and that's what's happening in Simon's problem. Like all the gigantic hypercube was split up into these little pairs, x and x plus L, that got the same color, and otherwise colors were distinct. And you had to figure out L. Okay, or in period finding over Zn, H was again, in that case, sort of promised to be generated by a single element. So H would look like this. This is like a subset of Zn. Okay, and the translates look like, the cosets look like x, x plus L, x plus 2L, etc. And again, you had to basically identify H. In other words, its generator L. Okay, but now in this framework, you can now finally talk about the hidden coset problem, or the hidden subgroup problem over the symmetric group, or the hidden subgroup problem over the dihedral group, or so forth. So for example, just to say it really briefly, the hidden subgroup over the hidden subgroup problem over the dihedral group, it basically boils down to the following. You can basically assume that the subgroup is generated by a reflection. So it's like you have a function on the cycle where there's like a secret reflection that you don't know. And your function, which assigns a color to each vertex on the cycle, like red, green, blue, etc., it pairs things up. So this will also be red, this will also be green, etc. And your task is to figure out which is the reflection out of the capital N, which you think of as exponentially many possible reflections.
Is that very different from the Simon's?
It's different somehow, yeah. I mean, it looks similar, but I don't know, there's more structure somehow in Simon's problem. But the fact that it's not that terrible looking is somehow the reason why Kuperberg has at least a non-trivial quantum algorithm for this problem. Okay, so in the last, don't have much time, but I'll say a few minutes. I'll say about how to try to solve it quantumly. So you could try to solve this problem in a general group by basically applying Simon's algorithm. Okay, so what do? You prepare the uniform superposition over group elements. Okay, and again, you have to take a little bit of care about how group elements are represented as bit strings, but not worry about that much because I don't have that much time. And then you're going to stick in some zeros here in the output register. And then you're going to pass this through QF. This is what we always do, kind of. Okay, and so you load all of F's values into some state. Okay, and then you're going to measure this. This is what we, again, always have done. Okay, and so that picks out a particular color at random, which is basically equivalent to picking out a coset at random, right? Because the story is that your group G is divided into these cosets, and they each have a different color. So you kind of pick a color at random, and then it collapses to the uniform superposition over all the group elements that have that same color, i.e. that are in that same coset. So I'm going a little bit fast here, but it collapses to something that looks like this. 1 over the square root the size of the subgroup, or the size of the coset. All the cosets have the same size. The sum over all x in, let me say, G star H of x, where G star is basically a random group element. So this is like a random coset. Okay, so this does something you have no control over. Like when you do the measurement, it's effectively like a random coset gets picked, And then you get a uniform superposition over all group elements in that coset, all the ones that have the same color. Does that make sense? So this state is called the coset state. And it's sometimes notated just, I mean, they love to do this. G star H ket. Okay, this is like a long abbreviation for, or short abbreviation for this thing. Okay. Just remember here, I didn't say it very clearly, but again, the problem is H is like a secret to you. You don't know H. You're trying to figure out H. Okay, but like F is like periodic with respect to this H. So you've got into a situation where like the quantum state you have is like got some kind of structure with respect to H. It's sort of like uniform on all the group elements, or qubit descriptions of group elements that are in the coset. And actually, you get a random one of these states. So let me just make a little aside here. A long time ago, I told you that we'll eventually start studying not just quantum states, but probability distributions over quantum states. If you remember way back to like Alice and Bob and like the moon and Jupiter, like we were often looking at like the quantum state where like there's a half chance it was ket 1 and a half chance it was ket 0. That was a probability distribution over quantum states. And we actually have this situation kind of at the end of this measurement. Oh, sorry, this is called a mixed state. And we have exactly this scenario. We have the uniform probability distribution over the different coset states. So in some sense, we have like a mixed state. And so we'll eventually see in this course, we're going to talk about mixed states a lot. And somehow they're like the real notion of a quantum state. Like, this kind of like, ket stuff, like that's like the warm-up notion of a quantum state. The real notion of a quantum state is these mixed states. But we've kept it simple for a while. But this is a little bit of motivation for thinking about these probability distributions of our quantum states. So like what we are holding on to now, if you take this broad-minded view, is what's sometimes called rho H. It's the uniform distribution over all the coset states GH. And there's this many of them. There's a lot. And if you think about it this way, then the situation so far is, with a quantum circuit and the ability to implement this mystery H periodic function, we have the ability to generate this mixed state. And it's a different mixed state for different H's. And H is the thing we're trying to figure out. And so we're kind of asking, like, given the ability to generate this state, can we learn what H is? I'll say more about that viewpoint in a second, but let me not think about it this way for a moment and go back to like the standard recipe that we had used for like Simon's algorithm and Shor's algorithm and so forth. So at this point in the standard recipe, this would be the point where we do the Fourier transform. And we saw it for the Fourier transform over this group. That was the Hadamard transform. And the Fourier transform over this group. That was the standard discrete Fourier transform. And we would basically, just skip over this, we would do the Fourier transform. And then we would measure. And this was sort of the Fourier sampling paradigm. And it would give us some kind of clue to H. Or in these two more familiar examples, to the L generating the mystery H. OK, in this case, period finding, we got like a random multiple of capital N over capital L. OK, and then by getting a few such clues and like GCDing them and dividing the result into N, you could discover L. And like in this case, you got like a random string that made a dot product of 0 with L. And so we did that like n times and got sort of like n linear equations about the bits of L, solved them, and discovered L. OK, so like in the commutative cases that we saw, commutative group cases we saw, we, with like a mild amount of ingenuity, figured out an efficient, algorithm for like taking clues and determining H. And it's a fact that it's proved subsequently to Simon and Shor that all of this is fine in all the finite commutative groups. As I said before, all the finite commutative groups kind of just look like cross products of these integers mod n groups. And like you have like an appropriate Fourier transform, like the Fourier transform for Zn1 cross Zn2 cross ... is like the discrete Fourier transform for n1 tensor, the discrete Fourier transform for n2 tensor, etc. And allow me to just say, long story short, you can efficiently do everything, the Fourier transform, the clues to H deduction in the commutative case. But, yeah?
So will you actually combine the GCD with the linear equations that you get for the product?
Yeah.
OK, so you'll combine two, OK.
Yeah. But, as I also said, in the non-commutative case, the Fourier transform, the appropriate Fourier transform exists. It's much more mathematically sophisticated. But luckily, thanks to people's hard work, we actually know how to implement it efficiently with a quantum circuit. But it's like this piece that totally stuck on, basically. OK, and so therefore, we don't know how to do efficiently the hidden subgroup problem over the symmetric group, which is a shame. It would have given us graph isomorphism. Or over the dihedral group. It's a shame. It would have given us this shortest vector problem algorithm. So we're kind of stuck. But perhaps someone can make progress. Let me end in 2 minutes by telling you, though, a different strategy you can try, which comes back to this picture. This is a strategy due to Ettinger, Hoyer, and Knill in 2004. And you can think of them saying, OK, let's forget the Fourier stuff for a minute. Let's just stop here and say, look, we have the ability to create this mixed state, this probability distribution over quantum states. And at this point, we know we create this probability distribution. OK, so we know we can efficiently create rho h. And we know there's, which is one of these possibilities. So either rho h1 or rho h2 or rho hm, where h1 through hm are all the subgroups of G. And so now, just given the ability to create, let me call samples of this state, quantum state, we have to figure out which one of these it is. And this is actually extremely analogous to a classical statistics/learning problem called hypothesis testing. So let me tell you the classical analog. In the classical analog, you have the ability to get samples from a probability distribution, just like a normal probability distribution over whatever, let's say binary strings. And you know it's one of m possibilities, and you get samples from it. These are like your hypotheses for which it might be. And you're trying to guess which one it is. Okay, that's an extremely standard like stats problem. And it's not hard to show in classical probability statistics that if your hypotheses are in some sense sufficiently distinct, sufficiently far apart, you can figure out from your samples from your classical distribution which hypothesis it is using something like log m samples. With high probability, log of the number of hypotheses is enough information theoretically to determine which probability distribution you have. Information theoretically, not necessarily with an efficient algorithm, but at least information theoretically. And it turns out it's going to be exactly the same in the quantum world. If these quantum mixed states are sufficiently far apart for a notion of mixed state distance, which we'll get into later in this course, fidelity, you can again do this like sort of hypothesis testing problem using only log m samples or log m copies of this mixed state. And it's a fact that how many subgroups are there? There's always at most cardinality of g to the log cardinality of g subgroups of any g. That's not too hard to prove. Basically, because every subgroup is defined by at most this many generators. So there's only like g choose that many different possibilities. So this is like our m. And so log of m is like log of g squared, which is what we kind of like to call like log of little n squared. So this is what these people proved. They actually proved that if you just use your QF about this many times, which gives you an efficient quantum circuit, you'll have enough samples such that if you very cleverly measure them, you can statistically determine which one of these states it was, and thereby learn H. The trouble is, it's sort of statistically or information theoretically enough information, but we don't know an efficient algorithm, like a computationally efficient algorithm, for figuring out which it is from the samples or the copies. So on one hand, you might say, well, it doesn't work. It's not good for anything. But well, again, like maybe we'll figure out a strategy that works in this way. And I also just wanted to tell you this story because I think it motivates the study of mixed states and quantum probability and quantum statistics and hypothesis testing and quantum state learning, which are all things that we'll talk about in the latter part of this course. OK, so see you on Tuesday.